Welcome to the Radar and Electronic Warfare channel. In this channel, you will be learning a lot of useful information about radar and electronic warfare systems. Stay with us and please click like and subscribe. In this episode, we will be discussing an introduction to radar systems and how they were developed through the years to modern time. From the dawn of civilization, humans relied on their eyesight and optical devices to observe objects that were far away. Obviously, there were many limitations to that, such as light conditions, visibility conditions due to weather, etc. As technology progressed, humans discovered that with the use of electromagnetic radiation, it was possible to observe objects at a great distance, regardless of light conditions and visibility conditions. The radar was born. The word radar is actually an abbreviation and stands for radio detection and ranging. A radar is a sensor which uses radio waves to detect an object and can determine object parameters such as bearing, range, and radial velocity. Radars can be used for both military and civilian applications. Typical military applications include the detection and tracking of targets such as aircraft, drones, naval vessels, guided missiles, and soldiers. Radars can also be used for weapons guidance and control. Typical civilian applications include navigation, air traffic control, and meteorology. Beyond the typical parameters, special types of modern radars can provide extra capabilities to the users, such as target height, 3D radar, terrain mapping, synthetic aperture radar, and target shape, inverse synthetic aperture radar, for which we will talk in other episodes in our channel. The technological evolution in the fields of digital electronics and signal processing is expected to provide further capabilities to the radar systems in the future, including greater resistance to countermeasures. Early experiments. In the 1880s, the famous physicist Heinrich Hertz experimentally proved that conducting objects can reflect radio waves, according to the theory of the prominent scientist James Clerk Maxwell. In his experiments, Hertz used radio waves at a frequency of 454.5 MHz with a corresponding wavelength of 66 centimeters. In 1895, Alexander Popov, a physics instructor at the Imperial Russian Navy School in Kronstadt, developed an apparatus for detecting distant lightning strikes and improved it a year later. In 1897, while testing this equipment for communicating between two ships in the Baltic Sea, he took note of an interference beat caused by the passage of a third vessel. In his report, Popov wrote that this phenomenon might be used for detecting objects. In 1904, the German engineer Christian Hulsmeyer obtained a patent for a ship detection device using radio waves, which is called telemobiloscope. His main purpose was to contribute to navigation safety by providing a device for ship detection in poor visibility and darkness. The trials were successful. However, the system was not adopted by the German Navy, mainly due to its relatively short distance. During the 2 decades between 1920 and 1940, most radar systems that were developed were continuous waves and transmitted in the VHF frequency zone 30 to 300 MHz. However, the frequency zone had some native restrictions such as poor angular resolution, inability to design relatively small antennas to transmit narrow beams, poor bearing accuracy, limited receiver sensitivity, etc. Additionally, the continuous wave radar didn't provide the ability to measure distance, but only the detection of objects. Measuring distance capability was added later with the development of pulse radars. The main achievements in the design and development of radar during the 1920-1940 period were the following. Guglielmo Marconi in 1922, in a speech delivered to a meeting of the Institute of Radio Engineers, later to become a part of Institute of Electrical and Electronics Engineers, spoke of the use of a radar type device on a ship to immediately reveal the presence and bearing of other ships in fog and thick weather, as he said. In 1922, two engineers of the U.S. Navy, Albert Hoyt Taylor and Leo Clifford Young, later staff of the newly founded U.S. Naval Research Laboratory, installed a portable experimental device on the banks of Potomac River that transmitted radio waves at 60 Hz frequency across the river to a receiver. When a passing vessel entered the radio wave beam, the researchers noticed an abrupt spike in the signal width of the receiver signal. The researchers continued to experiment and were convinced of the practical value of the device for detecting ships. Despite the promising results of this experiment, the US Navy did not sponsor further work at the time. In 1930, during some experiments conducted by the US Naval Research Institute, engineers Lawrence Hyland and Leo Clifford Young realized that it is possible to detect flying aircraft using radio waves. This observation took place during the testing of new direction-finding equipment for aircraft. However, the introduction of the pulse radar combined with a monostatic configuration, where transmitter, receiver, and antenna are all combined in one system, boosted the interest for more advanced radar systems. On April 28, 1930, the first radar echoes were obtained at the U.S. Naval Research Laboratory using pulses with a radar operating at a frequency of 28.3 MHz and a pulse width of 5 microseconds. The range was only 2.5 miles. By early June of 1930, the range was 24 miles. By June 1935, the British had demonstrated the pulse technique to measure range of an aircraft target. This was almost a year sooner than the successful Naval Research Laboratory experiments with pulse radar. By September that year, ranges greater than 40 miles were obtained on bomber aircraft. The frequency was 12 MHz. Also, in that month, the first radar measurement of the height of aircraft above ground was made by measuring the elevation angle of arrival of the reflected signal. In the United Kingdom, research started in 1935 to develop radar systems that would be used to detect incoming aircraft. The looming prospect of a war with Germany, as well as Germany's significant progress in the production of modern aircraft, expedited the process of the program funding. As a result, a network of a fully functional radar system by the name of Chain Home was installed by September 1938. The radar was operating in the frequency band of high frequency, 3 to 30 MHz, and while it had reduced accuracy in direction finding of the targets, they did continue decisively in the prevalence They did contribute decisively in the prevalence of the Royal Air Force during the Battle of Britain. Father of the chain home system was the distinguished British Robert Watson Watt. Britain developed a series of other radar devices during the Second World War. The US Navy installed the first production radar system CXAM and variants on few ships between 1937 and 1942. The CXAM and its variants operated at the 200 MHz frequency with a peak power of about 300 kilowatts. CXAM proved extremely useful. It included a switch to allow it to change its pulse repetition frequency, or PRF, allowing an operator to detect ghost echoes. Switching the PRF did not change a return from a to target, but it did cause a ghost target to jump to a new position on the display. Later on, this feature also allowed the CXAM to be used for secure communications. The switch was changed to a telegraph key, and two CXAMs could be used to trade Morse code messages over line-of-sight distances, with a narrow beam and relatively high frequencies, making eavesdropping difficult. The first radar of the US Army was the SCR-268, which operated at a frequency of 205 MHz and was used to improve the precision of anti-aircraft gunfire. For the development of this radar, US Army engineers took essential technical information from the US Navy's CXAM radar project. On May 26, 1937, a prototype was demonstrated and the radar entered service in 1940. About 3,100 systems were produced by the end of the war. By the end of the Second World War, the system was already considered out of date, having been replaced by other such smaller and more accurate microwave-based systems. Another US Army radar was the SCR-270 at a frequency of 106 MHz. Was developed during the same period with the SCR-268 and used for aircraft detection and tracking. The SCR-270 was one of the first operational early warning radars. It was the US Army's primary long-distance radar throughout Second World War and was deployed around the world. One of those radars detected the approach of Japanese aircraft toward Pearl Harbor near Honolulu on December 7, 1941, but the detection and report of the approaching enemy was not taken seriously, with the devastating results we all know about. The first Soviet design radar to survey the air situation was the type RUS-1, Reven, accepted into service in September 1939. It was experimentally tested in the Soviet-Finnish War. At the beginning of the Great Patriotic War, there were about 45 of these radars in the armament of the Red Army, mostly assigned to the Polish border and the Far East. After the Soviet-Finnish War, a prototype of the RUS-2 radar was also tested in combat, which was able to capture air targets up to the distance of 120 kilometers, and was accepted into the air defense armament in June 1940. Based on the experience from the operation of the initial series of this radar, a single antenna stationary modification of the RUS-2 Pegamtit and the mobile variant of the RUS-2 Red Dot, located in two boxcars 1,000 meters apart, were created. The development and improvement of the Red Dot radars resulted in a series of Pegmatit P1, P2, P2M, P3A, and P8 radars, which played an important role in Soviet air defense during the Second World War. Finally, at the beginning of the Second World War, Germany had progressed further in the development of radar than any other country. The Germans employed radar on the ground and in the air defense against Allied bombers. Radar was installed on a German pocket battleship as early as 1936. Radar development was halted by the Germans in late 1940 because they believed the war was almost over. The United States and Britain, however, accelerated their efforts. By the time the Germans realized their mistake, it was too late to catch up. The opening of higher frequencies in the microwave region to radar, with its attendant advantages, came about in late 1939 when the cavity magnetron oscillator was invented by British physicists at the University of Birmingham. In 1940, the British generously disclosed to the United States the concept of the magnetron, which then became the basis for work undertaken by the newly formed Massachusetts Institute of Technology, or MIT, Radiation Laboratory at Cambridge. It was the magnetron that made microwave radar a reality in the Second World War. Magnetron is the source of energy in the common microwave oven of our time. The successful development of innovative and important microwave radars at the MIT Radiation Laboratory has been attributed to the urgency for meeting new military capabilities, as well as to the enlightened and effective management of the laboratory and the recruitment of talented, dedicated scientists. More than 100 different radar systems were developed as a result of the laboratory's program during the 5 years of its existence, 1940 to 1945. The klystron was the first significantly powerful source of radio waves in the microwave range. Before its invention, the only sources were the Barkhausen-Kurz tube and split anode magnetron, which were limited to very low power. It was invented by the brothers Russell and Sigurd Varian at Stanford University. Their prototype was completed and demonstrated successfully on August 30, 1937. Upon publication in 1939, news of the klystron immediately influenced the work of US and UK researchers working on radar equipment. One of the most notable microwave radars developed by the MIT Radiation Laboratory was the SCR-584, a widely used gunfire control system. It employed conical scan tracking, in which a single offset squinted radar beam is continuously rotated about the radar antenna central axis, and with its 4-degree beam width, it had sufficient angular accuracy to place anti-aircraft guns on target without the need for searchlights or optics, as was required for older radars with wider beam widths, such as the SCR-268 mentioned before. The SCR-584 operated in the frequency range from 2.7 to 2.9 GHz, known as the S-band, and had a parabolic reflector antenna with a diameter of nearly 6.6 feet or 2 meters. It was first used in combat early in 1944 on the Anzio beachhead in Italy. Its introduction was timely, since the Germans by that time had learned how to jam its predecessor, the SCR-268. The introduction of the SCR-584 microwave radar caught the Germans unprepared. Post-Second World War developments. Monopulse tracking radar. The first monopulse radar was developed at the Naval Research Laboratory in 1943. In order to provide better accuracy than conical scan tracking radar, better resistance to jamming, less susceptibility to receiver noise and target radar cross-section (RCS) fluctuations. It can theoretically obtain the angular error with the transmission of a single pulse, practically with 2 or 3 pulses. The first prototypes had to overcome several technical problems, so the first monopulse radars with high accuracy were produced during the 1950s. A typical example is the C-band AN FPS 16 tracking radar. Today, the monopulse radars and the associated technique are still in use for precise target tracking. Moving Tracking Indicator MTI radar. It can reject the stationary targets and clutter, and thus present only the moving targets to the operators. Before the introduction of the klystron tube, which provides coherent pulses, early MIT systems had to use the so-called acoustic delay line in order to reject the stationary targets in the display. The introduction of phase-coherent klystron transmitters, as opposed to the incoherent cavity magnetron used on earlier radars, led to the introduction of a new MIT technique. In these systems, the signal was not fed directly to the display, but first fed into a phase detector. Stationary object did not change the phase from pulse to pulse, but moving objects did. Phase coherent signals also allowed for the direct measurement of velocity via the Doppler shift of a received signal. Further post-war developments. Electronically steered phased array radar. It can steer the radar beams electronically without the need of antenna rotation, thus eliminating any errors produced by the mechanical motion of the antennas. Simultaneous electrical scanning in both azimuth and elevation was first demonstrated in a phased array antenna at Hughes Aircraft Company in California in 1957. Synthetic aperture or SAR radar first appeared in the early 1950s, but it took almost 30 more years to reach a high state of development with the introduction of digital processing and other advances. SAR or SAR is a form of radar that is used to create two-dimensional images or three-dimensional reconstructions of objects, such as landscapes. SAR uses the motion of the radar antenna over a target region to provide finer spatial resolution than conventional stationary beam scanning radars. SAR is typically mounted on a moving platform such as an aircraft or spacecraft, and has its origins in an advanced form of side-looking airborne radar. Invest synthetic aperture radar, or ISAR, operates under the same basic principles as SAR, but with one key difference. The ISAR uses the movement of the target itself to generate its reading, rather than the movement of the radar emitter. ISAR is used in military and space applications for identifying and targeting objects by their movement. Since 1970, advances in digital electronics, including solid-state technology and signal processing, has provided the means for developing higher performance radar systems in terms of technical and operational capabilities. The main groups of these radars are summarized below. Multifunctional naval radars for detection, tracking of multiple surface air targets and weapon guidance. Airborne surveillance and reconnaissance ISAR radars. Ground radars for air defense, including the detection and tracking of ballistic missiles. Airborne pulsed Doppler radars. Advanced weather radars. Modern HF radars for long-range detection. Bistatic multistatic radars. Low probability of interception LPI radars. Modern marine radars. Thank you for watching our introduction to radar systems. Please don't forget to like and subscribe to our channel.